Welcome back. Let's continue investigating the end behavior of functions, focusing on what happens to a function's y value as its x value approaches negative infinity and positive infinity. We had looked at two examples. Let's look at two more examples and record their end behavior. Let's go to our notes screen. Our first of these last two examples is the function f of x equals 1 over x minus 3. Just like we saw with our first two examples, we have two basic tasks. I want to graph the function by creating a table of coordinate points. So we'll begin with a table. And recall that that left column we'll call x, and the right column will be f of x. And for this function, let's choose our domain values -2 through +2, but then let's extend it a bit further. Let's keep on going to 5. And at this point, we've got our table set up. So we want to just evaluate the output. What's the y value, for instance, when x is -2? So we're looking for f at -2. And we'll just substitute into the function and compute this manually. So this is 1 over -2 minus 3. I've just replaced the x with -2. That simplifies to 1 over -2 minus 3 is -5. And as a decimal, that's -0.2. So we'll record that point here as -2, comma, -0.2. We'll keep going, f at -1. And similarly, we'll just substitute that x with -1 minus 3 as part of the function rule. And that gives us 1 over -4, or -0.25. There's a second point that we can graph, -1, comma, -0.25. F at 0 is 1 over 0 minus 3, which reduces to 1 over -3. As a decimal, that's an infinite repetition. So -0.3 bar, that 3 continues forever. Notice with these x values that as we get closer to the origin, the y values get smaller and smaller. Let me record that better. -0.3. So they go kind of down from the x-axis. We'll really be considering the reverse when we think about the end behavior. Let's get the graph first. So next value is f at 1, which is 1 over 1 minus 3, which reduces to 1 over -2, or -0.5. At f at 2, we'll substitute 2 for x, so 1 over 2 minus 3, which is 1 over -1, which reduces to -1. So you can see the decimals are now resolving into a -1. So at 2, we're at the value -1. Next x value is 3, so we'll calculate f at 3, which is 1 over 3 minus 3, which is 1 over 0. Now we got to think, am I permitted to divide by 0? No, not today. And we'll record that as an undefined point. Undefined. So at this point, we're savvy about rational functions, and we know that they have a vertical asymptote when that denominator is 0. So we can actually plot that at 3. The great divide in the rational function. Well, let's see if we have a defined value when x is 4. So f at 4 is 1 over, again, I'm just replacing x with +4, so that's 4 minus 3, which is 1 over 1, and that's a good point, 4 comma 1. Last value that we've got here on our table is x equals 5. We'll calculate f at 5, which is 1 over 5 minus 3. And that reduces down to 1 over positive 2, or positive 0.5. So we've got our points. We're going to graph them at this time. So we'll start here on the left at -2, and that's at 0.2, so very close to the x-axis. 1 is also very, very close. 0 is down at -1/3. 1 is at -0.5, and 2 is at -1. So we can see that left side departing down from the x-axis as it gets close to the vertical asymptote at x equals +3. When we jump over to the right side of the vertical asymptote, we have the point 4, 1. And then the last value we had calculated was 5, 1/2. Let's sketch that curve. So definitely this left side starts very close to the x-axis on the left. We'll use that in a moment to describe the end behavior. The right side starts being very close to that vertical asymptote and then assumes a position very close to the x-axis as it heads over to the positive x values. So that first task is complete. We have graphed the function. At this time, we want to describe the end behavior. So remember, we're starting saying what happens to the y value when x gets close to -infinity. So really we're saying what happens to the y when we go very far to the left. So as x approaches -infinity, what y value is these points over here on the left getting closer and closer to? And you can look at these y values in our points from the table. As we go more and more negative, which was higher and higher up in the table, what value are these y values getting closer and closer to? See if you can predict. Excellent. As x gets more and more negative, y gets closer and closer to 0. Let's now finalize this task by describing the other side of the graph. So as x gets closer to +infinity, we also want to ask what happens to those y values. As x approaches +infinity, y approaches, again, let's investigate in the table. So we don't have as many points on the far right side as we did on the left, but you can see that they're very symmetric, just opposite signed. So the pattern is the same, it's just we're approaching the x-axis from the positive side. In any case, as x gets bigger and bigger and bigger, y gets smaller and smaller, closer and closer to 0. Okay, so that completes that example with f of x equals 1 over x minus 3, a nice rational function. Well, let's complete our example set for describing end behavior of functions with this last f of x equals -x cubed. So we'll begin again by creating the graph from the table. And let's think about what we can choose for our x values. So I'm going to notice that this looks like one of our parent functions, positive x cubed. So this is -x cubed. Let's see if our traditional -2, -1, 0, 1, and 2 will be enough for our graph. So we'll start by evaluating f at -2. And just like we did in our previous example, we're going to just substitute -2 in for x. Notice I'm putting parentheses because I have a double negative. That first negative is actually from the rule, from the function rule. The second negative is from the x value itself. So I got to represent both. Parentheses help me with that. So that becomes, let me fix this. I've got it looking like an exponential function right now. but that exponent should be specifically 3. So let's cube -2. So this is negative times -2 times -2 times -2. So we'll just resolve this interior first. So that's 3 negatives. That's going to be a negative product of -8. -8 becomes +8. So our first point here is -2, +8. We'll keep going. F at -1 is negative parentheses -1 cubed, which again is negative on the outside, and then 3 negative 1s multiplied. So the negative 1s on the inside, -1 times -1 times -1 will give us a -1. And then the negative on the outside makes that positive. So we've got a second point, -1, +1. F at 0 is -0 cubed, which is -0 times 0 times 0 within the parentheses. We don't have to do a lot of calculation there because one of those zeros multiplying would be enough to make the whole product 0. So we've got the origin. Let's calculate f at +1. That's negative +1 cubed. So that's negative times 1 times 1 times 1, which is just 1, times the negative is -1. So here we actually have a negative output, so 1, -1. And you can kind of see a somewhat symmetry here in the values, if not in the signs. See if you can predict what the output for f at 2 will be. It's -2 cubed, -2 times 2 times 2. That inner product's going to be 8. Negative makes it -8. Did you say -8? Good. 2, -8. So now we're ready to plot our points and to graph that function. So -2 is at +8. -1's at +1. 0, 0, 1, -1, and 2, -8. So we've got that framework for the function. Now we just need to sketch it and connect everything. So as part of this task of graphing functions, I know we're just working from a table here. You can always check your shape of the function by graphing it on desmos.com and using that as a cross-reference just to ensure that the function you're putting within the framework of the points from the table matches the actual graph. So we are kind of focusing here on calculating by hand, but it's good to check with the graphing calculator just to ensure that the graph is accurate. Let's complete the second task then. So we've got a good graph here. I want to determine the end behavior as x approaches -infinity and as x approaches +infinity. So again, we'll pick up and just indicate where we're headed in the x. So -infinity is far out to the left. And remember on the table, that's these values at the top. So we're saying what happens to those y values as x gets more and more negative. In fact, heads out forever to -infinity. As x approaches -infinity, heads over to the left, the y values, and I'm really looking right here on the graph, the y values increase forever. We can see that that left-hand side of the graph is just going up, reaching into the sky. How would we describe forever in the y? That's infinity. Good. And our last task is to say what happens as x approaches +infinity. So we'll indicate there on the graph, we're looking at the far right side. What happens as the x values move to the far right side? And again, from the table, we're looking down here. What happens to those values of y? And on the graph, we're looking there. As x approaches +infinity, y approaches really more and more negative values. It's It's going down, 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 down. It's sending a root down into the earth. What would we call that? Forever decrease is negative infinity. So that wraps up our second example here, our fourth example in this set, looking at describing the end behavior of graphs. So what's happening to the y value as x approaches negative infinity and x approaches positive infinity. Thank you for joining. See you next time.